كمل دكتور.
Yeah, doctor, we hear you.
Probably you need to turn off your microphone.
Doctor, I sent to you on chat, please. Link of Google Meeting.
I already joined the Google Meet. No, but my voice gets echoed. Okay. Actually, my voice gets back. I can.
Can you check, Doctor, now, please?
Yeah, the voice, the quality of voice is not well because I hear my voice again and again.
We are all students in Google Meeting. Turn off them microphone.
Yeah. So for those brothers and sisters who are on the Google Meet, can't you join the other link? You know, brother Hassan is joining us again. Oh, okay, that's great. Brother Hassan, again, if you turn off your microphone, you can go ahead. Okay, so
now, Doctor, can you try, please?
Now, no, again, I can hear myself. Again, brothers, like I said yesterday, we will continue our discussion. If you remember, last week we talked about 1.1, 1.2, 1.3 last week, and yesterday we talked about 1.4, and now it is we are discussing 1.5. This is what you are supposed to be ready for the exam. You need to go through all of these, all of the subsections of section 1, and for the exam it would be fine if you are ready to solve questions from this one. And at the end of each subsection there are a number of exercises in the book, and you need to try to solve them yourself. It is not a formal assignment, but if you can do that, I'm sure that you are able to handle the exam. So okay, so this is 1.5 solution sets for a linear system. Yesterday we talked about this homogeneous. I try to go very quickly because yesterday we went through slide number 6. So a homogeneous system can be written as AX equals to 0. Remember that X and 0 are vectors and A is a matrix. And this always has a solution because if you replace X with vector 0, that would be one solution for that. This solution is called a trivial solution. But the important question is to find the non-trivial solution. I mean, other than 0. If there is another solution for that other than 0, we are asked to find that solution. For instance, this is an example. Determine if the following homogeneous has a non-trivial solution. So again, if you remember augmented matrix, we try to make the augmented matrix from this. So we have these coefficients and 0 at the right. So we can write it down this way. So A, this is a matrix, and a vector 0 in the last column. So this is like that. Okay, so this is the last column, and these are the coefficients of that. So if you use some row operations, yesterday we discussed it again. I'm not gonna go through that. At the end, we are left with this solution. 0 equals 0 means the system is consistent. So for this one, we can write it down. X1 equals to 4 by 3, x3, and x2 is 0, because x3 is a free variable. So these are the answers. X2 0, x1 4 by 3, x3, and x3 is 0. Sorry, x3 is free. It means that you can replace x3 with any value that you would like. It is a free variable. And based on that, the value for x1 is determined. So this is a solution, and a geometric representation of that for a span. If someone asked yesterday, a span of a V, look at this one. This is vector V. And a span means going forward and backward through this line. This is the span of V. Span or generate, I mean, if you would like. Okay, so yesterday actually we were at this point. So we continue our discussion from yesterday. The equation of the form x equals to su plus tv. Again, remember, x is a vector, u is a vector, and v is a vector, and t and s are two scalars or real numbers. It's called the parametric vector equation of the plane. Just remember the example that we just solved. In example 1, the equation x equals to x3v, when x3 is a free variable, or in other words, we could write it down like x equals to tv is a parametric vector equation of the line. So whenever a solution set is described explicitly with vectors in example 1, we say that the solution is in a parametric vector form. Just go back to the example. I mean this one. For instance, when we are write it down like this, or write this, for instance, x is x3 times v. So this is called the parametric vector equation, or parametric solution for that. Look at this example. So when a non-homogeneous linear system has many solutions, so now we are talking about non-homogeneous. So this means that A So for the homogeneous, we have this equation, ax equals to 0. This is for the homogeneous. But for the non-homogeneous, we have this one, ax equals to b, not 0. So look at this example. Example number 3, describe all solutions of this equation, ax equals to b. See, this is called a non-homogeneous equation. And A is this matrix. This is exactly the same matrix that we had in example 1. So to make it easier to follow the discussion, this example number 3 uses the example number 1. I mean, this is the same matrix that we had, we already saw. So A is this matrix, and now the B, the vector B is this one, 7, -1, -4. So we are supposed to solve this equation, ax equals to b, and we are supposed to find the values for x. So again, you need to be very confident to do row operations. You need to make many exercises. There are a number of, there are 3 row operations. If you remember, you can multiply one row and add it with another one, and interchange 2 rows, and scaling or multiplying a row by a scalar. So these are 3 row operations that we already saw. So row operations on this matrix A, we have this matrix A, and for the last column we have the value of B. So if you remember, okay, so this is matrix A, and this column is B. Again, going back to this one, look at this one, 7 -1 -4. So 7 -1 -4. This is the last column. So if you do some row operations, we already saw that this was the reduced form of the matrix by using some row operations, and the corresponding last column will be -1, 2, and 0. If you follow those steps, I'm not gonna go through that once again. So we come to this one. Is 1, 0, -4, -1. 0, 1, 0, 2, 0, 0, 0, 0. So first of all, look at the last one. So this corresponds to 0 equals to 0, which is okay. So this means that the system is consistent. And again, just please pay attention that the first column corresponds to x1, the second column corresponds to x2, and the third one corresponds to x3. So here this means that and x3 is free. This means that you can have any number that you would like and replace it for x3. So this is a way to solve a non-homogeneous equation. Okay, so if you write
excuse me, doctor.
Okay, sure.
Now, if I use 3 for x3, divide, I mean, yeah, 4 divided by 3, x3, so it will be 3. So x1, it will be 3. It's okay, right? Also it's...
No, why 3? You
if I
can
use now your repayment x3 by 1, right?
have any number. It replaces
Yeah.
it for
So if I
x3.
use 3,
For
I will
instance,
use 3.
so
It's okay, right?
what would be, you are going to replace x3 with
3.
what number? 3?
3.
Okay. For instance, yeah, I mean, this is one solution for that. So 3 means 4 minus 1, 3. Yes. For this one, if you replace x3 with 3, x3 will be 3, x1 will be 3, and x2 will be 2. But this is just one solution for that, right? Because
Okay, thank
you can add, for instance, x3. I would like to put it like x3 equals to 9. So then in that case, 9 by 3 becomes 3. 3 times 4, 12 minus 1, 11. In that case, another solution will be like x1 is 11, x3 9, and then x2 is 2, right? So there are infinite solutions for that. Infinite solutions. So this is one solution, this is another solution, and there are infinite solutions for that. You can have like x1, for instance, x3 equals to 0, for instance. It would be minus 27. I mean, it could be minus 100 plus 200, and any number that you would like. So because this is a free variable, so based on that, you can determine the value for the other variables. Okay, so if we are going to write it in a more fancy way, vector x is x1, x2, x3. So for the x1, you have this one, minus 1 plus 4 by 3 x3. For x2, we know that the value is 2. And for the x3, we put it right down like this, x3, because it's a free variable. So if you factor x3 for this one, so this term has x3 and the first one has x3. So we factor this one x3, then we have 4 by 3, 0 and 1, and plus this one, minus 1, 2, and 0, because this is like this one, 0 plus x3 and 2 plus 0 x3. So look at this one, brothers and sisters. See, this can be written down or decomposed to this one. Minus 1, 2, 0. Minus 1, 2, 0. And if you factor out x3, we have 4 by 3. Then this one, 0. And for this one, 1. 1 times x3. So we could put it right down like this one. So P is just a vector. P plus x3 times V. I mean, this is a parametric form of the solution. We can write it down like this one. This is just a fancy way to do that. So x equals to P plus T V. This is a solution for that. And we have the relation between non-homogeneous and the corresponding homogeneous solution for that. Because for the homogeneous one, the answer was just x equals to TV. And for the corresponding non-homogeneous, we have x equals to tv plus another vector. So this is the result. Thus, the solution of ax equals to b are obtained by adding the vector p to a solution of ax equals to 0. This is the corresponding homogeneous one. This is just another discussion for that. So we go from this one. And this is the geometric representation for that. So we say that V is translated by P to V plus V. See the following figure. So this is vector P, and this was vector V, and the result of V plus P means adding this one. You can have P here, and then adding two vectors will be this one. So the result of adding two vectors will be like this one. This is the answer, V plus P. So V plus P. This is just a geometric representation for the solution. We skip from these discussions because we have some more important discussions. Okay. So this is just a summary of our discussion. Suppose that the equation ax equals to b is consistent for some given p, and let b and let p be the solution. Then the solution set of ax equals to b is a set of all vectors of the form p plus vh, where vh is any solution of the homogeneous equation. I mean the corresponding homogeneous equation. So this is a summary of what we discussed. Writing a solution set in the parametric vector form. That we just saw an example from this one, but this is a formal procedures. First of all, row reduce the augmented matrix to reduced echelon form. Row reduce the augmented matrix. Augmented matrix, you have coefficient matrix plus the column, the last column corresponding to the right side of the equal sign. For the homogeneous one, it would be all 0, and for non-homogeneous, it could be any number. I mean, we refer to that as vector B. And then express each basic variable. Again, basic variable, you need to find basic variables. You remember that the basic variables are those variables which have a pivot column or pivot position. Those are basic variables, and if a column doesn't have a pivot position, it is called the free variable. So express each basic variable in terms of any free variables. We just saw in the example, x3 was free, if you remember. Write a typical solution x as a vector whose entries depend on free variables. In the example, it was x3. Decompose x into a linear combination of vector using a free variable as parameters. This is exactly what we just did. Okay, so this was chapter number 1.5. So, okay, brothers, we are done. We started from 1.1 through 1.5. Okay, so we discussed this one. And the next chapter, 1.6, this is just an application. We won't be going through this one because it talks about some applications in some, I don't know, physics or chemistry or any other one. We won't be covering this one. So for the exam also, you don't need to go through this one. So 1.1 through 1.5 and then 1.7. Okay, so we skip number 1.6. If you go through the book, you will understand what I'm saying. So the most important section after that is called a linear independence. Very important discussion. So an indexed set of vectors v1, v2, v3 through vp in Rn. Okay, so brothers, when we say that this is in Rn, what do I mean? For instance, if I say v1 is in Rn, means that v1 can be written down as this one. For instance, here we have v1, v2, v1, v2, and at the end it is vn. So this is the meaning of that. When we say that v1 is in Rn, means that it means that there are n number of real numbers here. So we would say that this is in Rn. So this determines then the number of elements here in the vector. So an index set of vectors v1 through vp in Rn is said to be linearly independent if the vector equation x1 times v1 plus x2 times v2 plus and so forth through xp times vp equals to 0 has only the trivial solution. If it has only trivial solution, then we would say that these vectors are linearly independent. Okay, so the set, in other words, the set v1, v2 through vp is said to be linearly dependent. This is the other way around. If there exist weights c1 through cp, not all 0. So if we can find at least one non-zero weight for that, this makes this set of vectors linearly dependent. But if we have only trivial solution or 0 solution, it is called linearly independent. So two important definition.
Could you repeat that, Doctor, please?
Repeat.
Yes, just the last note.
Okay, so again, let me remove everything here. Again, pay attention, please. An index set of vectors, v1, v2, v3, and vp, these are said to be linearly independent if the vector equation x1 times v1 plus x2 times v2 plus and so forth through xp times vp equals to 0, this is a vector equation. So if this equation has only trivial solution, we would say that these vectors are linearly independent. However, if we can find another solution, not all 0. So this means that there is some solutions which are not 0. In that case, we say that these are linearly dependent. So if we can find only trivial solution or 0 solution, this is called linearly independent. Otherwise, you would say that this is linearly dependent. Okay.
Thank you, doctor.
Okay, sure. Thank you. So look at this example. Very easy. Vector v1, 1, 2, 3, v2, 4, 5, 6, and v3, 2, 1, 0. The question is determine if the set v1, v2, v3 is linearly independent or dependent. Just solve this or answer this question. The set of these three vectors, do you think that these are linearly dependent or independent? It's not that easy to answer this question. We need to go through some steps to find a solution. So the question is to determine if this is an independent or dependent set of vectors. So this is the solution. We must determine if a non-trivial solution for the equation exists or not. To do that, again, we start with the raw operation on the associated augmented matrix. So these are the actually